Welcome to the Grandmaster series. I'm your host, the sometimes fast runner, but never really fast, Jim Scott. Today on the Grandmaster series, we'll be doing an in-depth performance analysis of the athletes competing in the 2021 Summer Olympics, with a focus specifically on the sports of croquet and tug of war. Wait, what? Are you serious? These sports haven't been in the Olympics for nearly 100 years? Huh. And we won't be covering the Olympics at all today? I'm sorry, everybody. I'm quite embarrassed by this mix-up. I'm told we'll be discussing instead GPU accelerated boosted trees and deep neural networks for better recommender systems. So given this new information, I'm reminded of a great quote by the discus throw's 4-time consecutive gold medal winner, Alfred Order Jr., who said, "I didn't set out to beat the world. I just set out to do my absolute best." And I think that embodies what we are here to talk about today. We'll be speaking with the world's leading experts in data science and explore their approach to winning the 2021 Twitter RecSys Challenge and how they used an ensemble learning approach to building their recommender system. I would also strongly encourage everyone to check out the paper that the team just published on this topic titled GPU Accelerated Boosted Trees and Deep Neural Networks for Better Recommender Systems. The link is of course going to be provided below in the summary. There are just a few things I'd like to point out before we get started. Anything discussed which is publicly available, including links to relevant content, will be shared in the video summary below. If you have any questions during the video, you can submit them through the chat. We'll try to provide answers throughout and at the end of the episode. And finally, please be sure to subscribe to our channel to be notified of upcoming videos in the Grandmaster series. Now, I'd like to introduce the Grandmaster Relay team. First, we have Chris Diott, Senior Data Scientist at NVIDIA. Chris has a PhD in computational science and mathematics with a thesis on optimizing parallel processing. Chris is a 4x Kaggle Grandmaster. Next up, we have Bo Liu. He holds a PhD in applied math and statistics from Johns Hopkins University. Bo spent time working in fintech and has earned his Kaggle Grandmaster's title. Gilberto, better known as Giba, is currently a senior data scientist at NVIDIA. Prior to NVIDIA, he worked at Opel, Airbnb, Petrobras, and Siemens. Giba had held the #1 position at Kaggle for more than 2 years. And finally, we have Benedict Schifferer. He's a deep learning engineer at NVIDIA working on recommender systems. He holds a Master's of Science in Data Science from Columbia University and previously developed recommender systems for a German e-commerce company. Now that the torch has been lit, we can get the first event underway. Chris will be starting the race with the baton. I'll be back at the end and provide closing commentary. On your marks, Chris, it's all yours.
Thanks for the baton, Jim. I'm really excited for this 6th episode of the Grandmaster series. Today, we're going to share NVIDIA's team's first place recommender system solution, and we'll be learning about GPU accelerated boosted trees and deep neural networks for better recommender systems. So today's work and the achievement of our first place solution is a collaboration between NVIDIA Merlin, the recommender systems, and NVIDIA Kagimon, the Kaggle Grandmasters of NVIDIA. The core team members who you'll meet in this show today are Benedict, Gilberto, known as Giba on Kaggle, Bo, Chris, myself, and other team members are Jiwei, Gabrielle, and Renee. So every year, the ACM conference on recommender systems hosts a recommender system challenge. So in 2021, data was nearly 1 billion tweets were provided by Twitter, and then with help of some additional universities listed here, the challenge was that given a tweet, you had to predict how the user behavior. So if someone saw a tweet, do they like the tweet? Do they reply to the tweet? Do they retweet the tweet or retweet with comments? So the challenge began on March 22nd and it ended recently on June 23rd. So how does one even begin to build a model to do this? What does the training data look like? So Twitter gave us nearly 1 billion, a data set with nearly 1 billion rows and 24 columns. And this is the information that we had to train our models. So you can see listed here, these are the columns. So each row in the data set is one interaction between a specific tweet and a specific user. And we also, in that row, we know how the user responded, whether they replied, retweeted, retweet with comment or liked. And we had to build a model from that. And here's a list of the columns. So you can see about a third of the features describe the tweet. So we have the text from the tweet. They actually gave us the BERT tokens. We have the type of tweet it was, whether there was media in the tweet, photos, videos, language of the tweet, timestamp of the tweet. We then have information about the author of the tweet. So in this whole video, we're going to refer to the author as the A user. And you can see in the data set, we were given stuff like their follower count, when their account was created. And then lastly, we have information about the B user. So the B user is the one who's reading the tweet. And this is the user we're trying to predict their behavior. What will they do? And you can see we have information about them also. So we build a model using all that train data, and then we submit our code to the RecSys server, and our code runs on a whole bunch of new tweets that we've never seen before, and it predicts what the user does. And we submit our code, and then we wait a few weeks, and we keep going back to the website where the leaderboard is, and then on June 30th, when we log on, this is what we see. Here's the leaderboard. On the top of the leaderboard, you can see NVIDIA Rapids AI Final Ensemble. So we're super excited. Our model was the most accurate. So the way the models are scored is so you're predicting 4 targets. And for each target, they calculate the average precision and the relative cross entropy compared to the true targets. And that's 8 categories. They sort of sum these up and rank them. And then lastly, I'll point out that this year, instead of they actually broke the predictions into 5 groups based on authors that are very popular, medium popular, low popular. They actually computed the metric per group, and then they averaged it all. So it's a pretty complicated metric, but in the end, you can see NVIDIA, if you just sum up our RCEs, we had 97.42. Second place was 93, and third place was 89. So we had a sizable lead over second and third place. So it turns out that the 2021 competition, the data was the same data structure and the same target types as the 2020 comp. So the competition in 2020 was also a comp sponsored by Twitter, and it was also, the task was to predict the behavior of a user seeing a tweet. However, there was notable differences. So no team could use their solution from 2020 and just use the same solution without changes in 2021. And let me point out the notable differences. So the training data was much larger in 2021. They went from 150 million rows, which are tweet user pairs, to 750 million. Also, all of the B users that you're trying to predict in the unseen test data, they exist in the train data. The train data was a longer period of time. We have 3 weeks instead of 1 week. And this next point is important. If you are on, this year you submit your code versus submitting predictions. And if you're familiar with Kaggle, this is the idea of a code competition. So last year we would, they gave us the test data without the predictions, and we would just predict on our own and then upload a CSV file. But this year we just upload our code, and then this allowed them to add limitations. They wanted to make sure that our code can run with limitations. So our code only had access to 1 CPU and 64 gigs of memory to make the inference, and it was limited to a 24-hour time period. And the last notable difference this year was, so for 2 months, we had just access to the train data and those labels. And then And when we submit, there's a public leaderboard, and that's our score against a valid test set, which if you're familiar with Kaggle, that's kind of like the public test leaderboard. And then in the last 2 weeks, they gave us all the targets for this validation set and the data. And then we were able to use it, train with it, whatever we wanted. So I'll point out here that these differences allowed us to do a lot of new things this year, including building some neural networks and doing some stacking. So the story today begins all the way back in 2020 when we competed in the competition, and you could see we won the competition in 2020. But as I said, we couldn't just reuse our code. So our solution in 2020 was an ensemble of 3 XGBoost boosted tree models. And the key to building these models was engineering very good features. And the way you make features is you have to just try features and see if they work. So an important component is having a very fast experimentation pipeline. So locally, we're able to speed everything up on GPU, and we could make a bunch of new features. We can train a model, and then we can calculate a local validation score. And we can go around this blue circle over and over and over and over, testing out lots and lots of features. And by using GPUs, we could essentially do hundreds of experiments in the time that you can maybe do one experiment on CPU. So through lots of experiments, we were able to find hundreds of great features, which made our 2020 XGBoost models really accurate, and they won the comp. And here was a little chart that we had showed last year in some of our papers that we were able to actually get a 280 times speed up by using Rapids, cuDF, Dask, XGB, and UCX over just using pandas and CPU. So we were able to leverage that this year. We were able to use that extremely fast pipeline to investigate lots and lots of ideas this year, which again gave us an edge. But as I said, we could not just use our solution from last year. So if you remember, last year was the ensemble of 3 XGBoosted models. And now on the next slide, I'm going to show you the picture of our solution this year. Whoa! So there's lots of models. There's a lot of stuff going on here. So this year we built 8 models. So it's kind of ironic, right? They actually added restrictions this year. They actually added restrictions on time limits and file sizes during inference. But nonetheless, we were able to build a big model and have it compute. And so it's 8 models. So you can see there's 3 neural network models and 3 XGBoost models on level 1. And those were the 6 models we built during the first 2 months of the comp, where we trained them on the train data. And then in the last 2 weeks of the comp, when they gave us access to the validation data, which for those of you that do Kaggle, that's like the public test data. When they gave us access to that, instead of retraining all of our previous models, what we did was we just stacked it. We just built 2 new XGBoost models, which took all the predictions of our old models, plus the original train data. And then we trained these 2 new models using this new test data. And this has many advantages. And Jiba and Benedict later will talk about the advantages of doing a stacking model such as this. But on this slide here, you can actually see the effect of doing this. So the table on the left, that shows all of our level 1 models. So we had 6 level 1 models, 3 boosted tree models, and 3 neural networks. These are the models that were only trained on the training data, which is 3 weeks prior, and that's all is before the test data. So when they predict the test data, those models were scoring leaderboard scores between 60 and 70, summed RCE. And if we ensemble them all together, we would get 80 RCE. Now, keep in mind, this is a time forecast, right? Because it's predicting into the future. Now, in the last 2 weeks, when they gave us access to the validation data, which I like to call the public test data, that data came from week 4. And that data is very similar in distribution to the actual test data or private test data that the competition wants us to predict. So you can see when we stacked our predictions through and trained it on this new data, we got a huge boost. If you look at the table on the right here, you can see that the individual level 2 boosted models were achieving 94, 95 summed RCE. And then when we ensembled those two together, it achieved 97.4. So huge accuracy. This is a really accurate model, which can be used in production to predict Twitter user behavior. So we have a lot of models here. We've got 8 models, and I mentioned the constraint. We have to upload these models with their embedding tables, with different feature engineerings in a zip file. Our zip file pushed the limit to full 20 gigabytes, and then our code was constrained to run on Twitter's server, which had 1 CPU core, and it used the full 24 hours. So we pushed all the constraints to the limit, but this was possible because what we ended up doing was we had to share some code between the models. So the original data is in a file, a TSV file, which contains the original tweet and other things. And so what we all did was we first loaded the TSV file, and we then created a whole bunch of common feature engineering, and then made a new Parquet data frame and wrote that to disk. And then later, all of the 8 models can then read the Parquet. So that way we all share some common features. Additionally, models have more unique features, but I'd like to talk about this common feature engineering because it's very impressive what we accomplished. So one of the main things we did in the common feature engineering was one of the columns was the tweet text, and it was provided as BERT tokens, which are numbers. So the common feature engineering would convert these numbers back into words, the tweet, and then we'd have to process this text. So we would search for certain words that appeared. We'd look at, what was the first word, what was the punctuation of the tweet. We would count @ symbols, see if it referenced other people or links in the tweet. So we had to search the text and find and break the text apart. And this is a really exciting news for Rapids. So Rapids, is it's a data frame library similar to Pandas, but it's fully on the GPU. And in recent versions, it can now process strings. So using Rapids, we could actually process millions of rows of data, and we were able to extract our common features in 1 minute using GPU, whereas it was over an hour if we did it on the CPU. And here's some example code, but for instance, this here is what the column of tweet text tokens looks like. So you can see it's this long string of numbers separated by this \T, which is a tab. And then using QDF, we first break this string apart into all the numbers. We then convert the numbers into their associated words. That gives us the text. And then using this code, we search the text for certain symbols, appearances of things. We can break the text into different pieces. And we did all this, and then we wrote it to a Parquet file, at which point all of the individual models can load it and use it. So now we have Bo, which is going to talk about our model's neural networks.
All right. Thank you, Chris. I'm going to talk about our neural network models. So neural network models are very competitive in this competition. In stage 1, our best single neural network model's performance is very similar to our best single gradient boosting tree XGB model. And the ensemble of the 3 neural network model beat the ensemble of the 3 XGB model by about 3 total RCE score. This is because the diversity between these 3 neural network model is larger than the diversity of the 3 XGB model. So all the XGB models, they use similar targeted encoding features with the same gradient boosting tree algorithm. but the 3 neural network models are designed and trained by 3 team members independently. So they differ in terms of the architecture, the training method, and even the deep learning framework. Can you go to the next? Here I'm showing the architecture of one of the 3 neural networks. So the other 2 share some common design. So they all have 3 modules. So on the left, the dashed square, inside is the NLP module using the tweet text. And in the middle is the categorical module using categorical features like A user and the B user, and the language and the tweet type. And the third module on the right is the continuous module using about 30 to 40 continuous features from the common process. The number of features is like slightly different between models. But for this model, it only uses the features from the common process, so no target encoding features. And also above the middle square, you see there's a matrix factorization block, which is a dot product of A user embedding and B user embedding. This is to represent their interactions. So the output of all 3 modules plus the matrix factorization are concatenated and then pass through MLP, multi-layer perceptron, which is just a few layers of fully connected layer, and finally output the 4 targets at the same time. Next. Here are some more details of the NLP module. So in order to use the tweet text, we initially tried variations of BERT, but even the BERT tiny, which is the smallest BERT variation, is too slow to infer on the one single GPU on the evaluation server. So we settled on a lightweight RNN, recurrent neural network. So it's actually the simplest possible RNN, a single layer, single directional GRU. Usually when people train RNN, they like to use traditional word embedding like word-to-vec or a glove embedding. But this time we used multilingual BERT's word embedding, which is the first layer of a pre-trained multi-layer BERT. So this has 2 benefits. The first is that the raw data is already come from in the form of BERT, multilingual BERT token IDs Chris showed, instead of tweet text. So basically the host already did the tokenization for us. So we can just directly look up the embedding without doing the tokenization during training. And the second benefit is that it's a multilingual BERT. So it's not only English. And in the data, the tweets come from like dozens of different languages. This is also multilingual. So it's a perfect match. You can see on this plot is the distribution of number of tokens per tweet. You can see many tweets have number of tokens more than 75 or even 100, but we only used the first 48 tokens for each tweet. This is for faster inference. So 48 is a hyperparameter. When we increase this 48 to a larger number like 64 or 80, the leaderboard score, the validation and the leaderboard score increase, but it takes much longer to infer. So in order to keep each single model's inference time under 7 or 8 hours, remember in total we only have 24 hours among all the models. So in order to keep single models inference time not too long, we settled for 48. The sacrificing some single model performance in exchange for more number of models. And the next slide, please. Okay, another big difference between a neural network and XGB model is that the XGB model uses target encoding features to encode user information, while the neural network uses user embeddings. So in this dataset, there are more than 25 million unique A users and more than 35 million unique B users. Now, target encoding, which Jiba will cover later, target encoding is just one number per unique user. But an embedding table has a dimension the number of row is the number of unique user, but the number of column is the embedding dimension, which can be 64 or 128 depending on the model. So the embedding table is much larger than the target encoding lookup vector. So this can cause two issues. One is that it cannot easily, the embedding table cannot easily, embedding table is part of the model. So if embedding table is too large, the model cannot easily fit on a single GPU. Another issue is that the model weights, when it's saved, it's just too large to upload to the evaluation server. So we have something like 20 gigabyte total the model size, total model size between all the models. So we did many optimization tricks to alleviate those problems. So the first trick is that we jointly embed A user and B user. So they share the same embedding table, but they are represented separately by two embeddings. So this is shown on the plot on the right. So this can save space because in the data set, A user and the B user, they have some interactions, meaning that a given user can sometimes appear as the tweet author and sometimes appear as the tweet reader. So which means that the union of A user and the B user, A user and unique B user is smaller than the number of A user plus the number of B user. So so this can reduce the size of the embedding table. Also, by sharing the same embedding table, the model can learn more about the users more efficiently. The second trick is to map all the low frequency users to the same embedding. This is also called frequency thresholding. So we use a frequency threshold of 3 or 5, depending on the model, meaning that if a user appears less than 3 or 5 times in this data set, either as a user or as a B user, then we call this user unknown user. And we group all the unknown users together as if they are the same single user. So this is going to just be one row in the embedding table. So this reduces the embedding table size to about 15 to 20 million rows, and which maxes out the GPU memory and the submission zip file size. The third trick is that we use sparse embedding layers in our PyTorch models. So the idea is that since the embedding table is large, embedding table is like 15 to 20 million rows, but for each mini batch, there's only 1,000 or 2,000 samples. So for each mini batch, only a tiny fraction of the rows gradients need to be updated, need to be calculated. So the gradient matrix can be stored as a sparse matrix. And this not only saves the memory on the GPU, but also can speed up the training a lot, because not all the rows gradient need to be calculated every batch. The speed up can be like between 3x to 6x. We're actually writing a technical blog post on how to do all these kind of tricks using NV Tabular. So please stay tuned for that. And the last trick of the embedding is that for one of the models, we split the 20 million users into two equal-sized 10 million row embedding tables, split the bigger table into two smaller tables, and train two separate models. And then at the end, when inference, we average prediction of these two models. And for the training, we use a trick called progressive training in one of the models. So we start with a high frequency threshold, which means a smaller embedding table to train for one epoch, and then lower the frequency threshold, which means increase the size of the embedding table and train for another epoch, and so on. And this can help the model converge faster. Some other training techniques we used include the AMP mix precision training and the multi-GPU training. And for the inference, we cast the model weight to float point 16 to make the model size smaller, and this doesn't affect the score. And lastly, I want to show some architecture differences of the other two models. So if you can go to the next, please, Chris. This second neural network model used some target encoding features. So it didn't embed a user. So it only embed a B user. And for this model, the matrix factorization is between the text module and the B user. Remember, in the first neural network model, the matrix factorization was between the A user and the B user. This model is between the tweet module and the B user. And also, in this model, it also outputs 3 additional heads in addition to the main head. And for the 3 additional heads, we calculate the accelerated loss in addition to the main loss. So the 3 additional heads are represented by the dashed lines. And finally, the last neural network model. Yeah, this one doesn't have a GRU component. So instead, if you look at the bottom left, instead, it does a mean pooling of all the text tokens. So this model is the fastest neural network model of the 3. And for this model, there are 2 matrix factorization. One is between the user, the B user, and the text, similar to neural network number 2. And on the right is between the A user and B user, similar to the first neural network model. And additionally, for this is the model that we split the 20 million embedding table into the 2 smaller ones. Because this model doesn't use GRU, it is the fastest, so we can afford to inference 2 times during the evaluation. Okay, now those are all the neural network models. Now I'm going to pass to Jiba. He will tell you all about target encoding and XGB models.
Okay, thanks, Bo. I'll talk a little bit about our XGB models, what's the idea behind them, and how we trained them. Next one, please. Okay, first idea. XGBoost models don't treat don't deal very well with categorical features, right? XGBoost models are built for numerical features. At least it's before version 1.3. After version 1.3, it's still in development, but it's possible to deal directly with categorical feature by using one-hot encoding directly inside the code, right, in real time. But in this data set, we have a very high cardinality features. For example, A user and B user have millions and millions of users. So in this case, XGBoost cannot deal with that kind of feature. Instead of that, we need some way to use that information from that feature, but without using that features directly as a number. Instead of represent A user as a number or B user as a number, we represent another way that the model can understand that. And to do that, the way we found is using the target encoding strategy. Next one. For anyone that don't know what target encoding is, this is a simple toy example on how it works. But basically, it's a transform function. When you convert a categorical feature into a numerical representation of that feature based on the target statistics, right? So in the left side, we can see a table with 3 columns. So B user ID column is basically the feature you're trying to encode as a target encode feature, right? And this in the middle column's target is it's a binary classification target, 0s and 1, and we are trying to represent that features based on that target, right? In the original idea of the target encoding, we just took the average of the target for each one of the categories we want to convert, right? So, for example, if you want to convert the B user number 1002 into a target encoding system, we just take the average of the target for that specific user, and then apply that results on the table on the right. So taking the average of that user, we got 0.5% probabilities of the target to happen. So we just replace that number on the table on the right, right? And this is very important for target encoding, is to split the data set in a trained part, in a valid part. So all the target encoding features must be made using out-of-fold predictions. That's what I represent here. I have a train data set on the left and a validation or test set on the right. So always use a train to encode the target encoded features and then apply the results to a validation set or an out-of-fold set of data to use the results. So basically, what we are doing here is we are replacing the numbers, the original numbers that represent the category, by the probability of happening each one of the categories, right? Next one, please. Here is a more advanced version of the target encoding when you're using something called smoothing. So what's the idea here? The original target encoding, you use only the average of the target. But actually, we have more information than that. We have the frequency information, or the count, of how many times each category happens in the train set, right? And we can use that information to add more signal to the encoded features. This is another toy example. I split it's exactly the same table as in the previous slide, but I added one extra column on the right called count, and that count is just counts. It tells the number of times each category happens in the train set, right? For example, the same user as before, user 1002 happens 2 times, so the number 2 is placed on the two rows in the train set, right? But what happens here? We are trying to smooth the target encoded based on the global average of the target. So the global average is just the average, the simple average of the target feature. In this case, it's 0.286. And what's the idea? The category that happens more in the train set is more reliable. What I mean, the value we got from the probability is more reliable. We can trust more on that value if you compare it with another category that happens only once in the train set, right? So what we are trying to do here is a weighted average between the original target encoding and the global average of the target. So that equation shows how the average can be calculated. It's pretty simple. To make it work, we need to add a smoothing factor parameter. I call S in the equation. Basically, if we set the S as 0, it becomes a plain average of the target as before, as in the slide before. But if you use any value higher than 0, it becomes a weighted average between the global average and the original target encoding, right? For example, the results of the target encoding with smooth are on the table on the right, on the column 4. And we can compare with the original target encoding without the smoothing factor. For example, the B user 1001 have a prior target encoding value of 1.0 or 100% previously, but after applying this smooth with a factor of 10, it decreased to 0.29, right? Why it happens? Because it approached the global average of the target variable, and it's very close to the global average actually, because the count in the original train set is only 1 for that category, right? And for the category 1003 on the train set, it happens 4 times, but every time it happens, the target is 0. But even having the original probability of being 0, the target coding with smoothing is 0.2 on the table on the right? So it takes into account the how many times it happens in the data set, and also the probability of the target in the data set. So it's a very clever way to encode and add more information to a categorical feature. Next one. This is a code snippet of calculating and applying the target encoding feature with smoothing. On the top, you can see it running in pandas, and on the bottom on QDF on GPU, right? They are exactly the same code on the top or in the bottom. The only difference is how you import the library to do that. But what I'm trying to show here is that it's pretty simple to apply a target encoding. Everyone that know pandas can do it, both on pandas or QDF. The biggest advantage of QDF is the speed. You can see that code runs in 1 second on GPU using QDF and 93 seconds on CPU. You may think why it takes 93 seconds on CPU. It's basically because B user ID is a very high cardinality categorical feature. It has 35 million users, and the original data set have hundreds of millions of rows. So in CPU, it have to compute it everything in a loop, and it takes really a lot of time. Next one, please. Okay, so now I told how targeting code works. Now I can talk about the XGBoost models. Why? Because we have 3 level 1 XGBoost models, and each model uses a different approach for targeting coding and strategy of training. For example, the XGBoost 1 model, the first one, it uses only week 2 and 3 of the train set to train the model, to fit the model. And even though it only sampled 40 million rows from weeks 2 and 3 of the training set, right? And this is how the model, the XGBoost model 1 is trained. But in total, actually, all the 3 models have a similar number of features. The biggest difference is how the target is encoded for the high cardinality features, and how the sample was taken from the original train set that comprises of 750 million of rows. So for this model 1, the target encoding also was calculated using leave one out strategy. What it means, for the train set, when calculating each feature, it leaves one row out, calculate the encoded for everything else, and then apply to that row that remains out from the calculation. The algorithm does it for all the rows in the training set to calculate using leave one out strategy, right? And also apply smoothing on the target encoding features. As I said before, target encoding must be applied on out-of-fold strategies. And the out-of-fold strategy here chosen was leave one out. Also, this model was trained using desk QDF that can scale, in this case, scale up to 8 GPUs. So it was used 8 GPUs at the same time to train the model. It reduced the training time to 2 minutes per XGBoost model. It's pretty fast, taking account the size of this data set. On the right, there's a code snippet of a data loading and a fetch function for XGBoost. If you are using it with XGBoost, you will understand that's pretty straightforward to use desk QDF to train a model. You basically just need to replace some function calls, and you need to add .desk in the call. Next one. The second XGBoost model is a little bit different. How the rows were sampling to be trained is very different from the first one. Basically, it was sampled 150 million rows from the original 750 millions. And actually, it was maintained, it was kept only the users in week 3 that happens on the previous week also. So we made sure that only old users are present in this data set. No new users on week 3 are present on this data set. We are able to discard almost 600 million rows just using that strategy. And that strategy is very similar as the strategy the organizers made to build the test set. So in test set also, all the users present on the test set are present on the train set, at least for the B users, right? So that strategy to sample the data from this model is pretty similar to what was used in the leaderboard. But also, this model run 3 bags with different seeds, and each bag uses 50 million rows of that 150 million rows. So basically, it was split in 3 different data sets and run one model for each one of that 50 million rows, right? So it's a average of three models, actually. Also, these models have pretty similar number of features, around 70 features. But the target encoding used in this model was calculated using k-fold and also smoothing. Remember, the model 1 used leave one out strategy, and this one is k-fold. It was trained on a NVIDIA V100 with 32 gigabytes of RAM. One important thing about that model is for submission, we have some constraints, especially based on file size. So we had to find ways to decrease the size of the files, especially the target encoding probability maps we use, because everything needs to calculate offline and send in the submission file, in the zip file, with everything pre-calculated offline, right? So in this model, all the target encoding maps were stored in int8 type instead of float 32 or int32. Why that? To save a lot of memory during the merge at inference, when merging that target encoding features with the train set, and also save disk size in the submission. To convert a probability to int8 is just to normalize the values to minus 128 to plus 127, and then typecast to int8, right? It's a trick but it helped a lot. Also, this model user ID was converted from int64, integer 64 to int32. It made some collisions between some users, but it's not the number of collisions were not enough to decrease or to hurt the performance of the models. One additional thing about target encoding in this model is it uses a multi-level target encoding, or a combination of features for each target encoding. For example, we can combine a user ID with language and tweet type feature, and you can combine it as it is one feature and then encode target encoding with that combination. On the right, you can see a code snippet of how to run that model. It's also pretty straightforward. If you know how to use XGBoost, you see there is nothing special in this code. Next one. The XGBoost 3 model strategy was different from the other 2 ones, especially the training strategy. It was trained on the last 20% of week 3 of data. So the data is very close to the test set, is the closest to the test set. And all the target encoded features were calculated using week 1, 2, and 8% of week 3. So everything is static and calculated using that data, and then applied to the remaining 20% in week 3 and to the test set on week 4. Also, that model has 69 features, very similar to the other XGBoost models, but the target encode features on that model were kind of special. They are different from the previous ones. It wasn't used the probability. Instead of probability, it was target encoded the sums of interactions and the count of interactions for each feature. It was also trained on NVIDIA V100, 32 gigs. In this case, the target encode maps were saved in int16 instead of int8, also to save disk space and memory at inference time. Another detail about that model, it was trained one model per target and also one model per group of users. Chris mentioned in the beginning that the metric is calculated for 5 groups of users. That groups were split based on number of followers of each user. So this model have 20 models trained, so 4 targets times 5 groups, 20 models. Also, another detail, that model was optimized for 1,000 trees, so the learning rate needs to be set to achieve the best results with 1,000 trees. So all the models have approximately the same size when stored to files. Also, it was using multi-level target encoding here. Maybe some of the features here have a lot of features that the target encode features. For example, the first target encode features have 7 grouped features or 7 combined features to encode each target encode new feature. Next slide, please. Here is an example of how it was target encoded the category for these XGBoost 3 models. Instead of using the mean, it was using the sum of the target. So on the table on the right, we can see that for each user, we have the number of interactions each user have made with each target, right? And also the count, how many times that user appeared in the train set. What is different from the other 2 models? In this model, we don't divide the sum by the count. We don't calculate the probability here. We use directly that values, and we leave to the model to choose the best smooth or the best threshold to use each one of these features. So basically, the model is being the one responsible to combine that features encoded by the target here. Yeah, the code snippet, you can see it's pretty similar to the previous ones. Next one, please. But also, we have a level 2 XGBoost models. We have XGBoost 4 and 5. And basically, that level 2 models are taking the data, the predictions from the level 1 models, both the XGBoost and the neural networks models as input features. So when we talk about level 2, we're talking about stacking and kind of ensembling technique to boost even more the results, right? And this competition was especially good to do stacking, how they provided the data sets, right? So in the top, we can see that we trained the models using week 1, 2, and 3. So we trained 6 models, 3 XGBoost, 3 neural networks. And then we are given the week 4 of the data set. So that week 4, we can use all the features released on that week 4, plus all the predictions the models generated from the week 1, 2, and 3. All the models trained on the previous weeks, all the predictions can be used as input for the week 4 model. So all our level 2 model were trained on week 4, right? So what we have as input for that model, we have the level 1 model predictions, 6 model times 4 targets, plus we have the target encode features that we build from the level 1 features using week 1, 2, and 3. Also, we are able to do counting and encoding, so we can also convert the categoricals using counting and encoding feature engineering. We can use a special technique here called a reverse user target encoding. What it means, for example, we can calculate the probabilities of A user and then apply the results to the B user feature. It's kind of you are calculating for all the probabilities for the user, the author of the tweet, and applying that results as a reader of the tweet, right? Is a kind of reverse target encoding. But also we can do that with the counting encoding. For the level 2, we can also do the target encoding of the tweet ID, especially because Ross said that some tweets ID can be shared between the public and the private test sets. Lead and lag features, we can sort by time and use what comes next and what came before. Use also original features in tweet token related features. So as you can see, the level 2 models have a bunch of features as input, also the predictions of all the other models built on the level 1. And what's the idea here? The idea here is to explore the diversity between all the level 1 models features. That's why we worked hard to build different XGBoost and neural networks models for the level 1. Just by training the XGBoost models using different time splits or different sampling strategies or maybe different target encoding strategies, we add diversity to the predictions of that models. And having that diversity in a stack and ensemble is essential to boost even more the scores in the end. Because if you build two very similar models, for example, using exactly the same features as input and exactly the same learning algorithm, then it brings no value to the stack. The idea is having diverse models as input to have diverse predictions and boost even more the results. Next one. Okay, Benedict, I pass to you.
Thank you, Juba, and thank you, Bo, and thank you, Chris, for all introduction. I will continue with the stacking model, and Juba already explained it in pretty detail. If you go to the next slide, Chris, please. I will summarize that. And the idea of stacking is that we can leverage the new data set. Often in production system, you get new data, you receive new data, and some techniques is fine tuning or continuous learning. And in our approach, we realized noticed that the best way is to stack our models, meaning we can use our pre-trained or trained stage 1 models from week 1 to 3 as an input. In addition, we built features on the trained data set, which you can see from the left corner box to the middle, and apply them to the validation data set. As Juba mentioned, it's target encoding or count encoding from the train and apply it to the validation. In addition, we can use the validation data set and create new features from it and apply it back to the validation data set, like count encoding or target encoding. And in the end, we built train-in-one model, which has the advantage to use the validation data set, the train data set, and the prediction from all stage 1 models to make the best choice how to predict in the end the private test data set. So if you go to the next slide. And yeah, we saw the slide already multiple times, and it's a complicated slide, but that's our final solution. I will talk a little bit more detail. So we have as an input our 3 neural networks and our 3 XGBoost model on stage 1. They are all trained only on the trained data set, and we feed them as an input, and then we train 2 different XGBoost models. They are pretty similar, but they use a little bit different features. They use different target encoding strategies, and then ensemble them again. So we have first the diversity in having 6 different stage 1 models, and then we have another diversity in having 2 different stacked models and ensemble them. And that in the end gave our best score. As Chris showed in the beginning, each of the stage 2 models had RC of 94 and 95, but combined they had 96 dot something, and on the public leaderboard even 97. And yeah, that's the advantage of our stacking. And we have like the diversity in like both levels, in level 1 and level 2. And one advantage is we don't have to retrain or continuous learning on the stage 1 models. We can all use them directly in our stage 2. That was our winning solution. If you go to the next slide. This is, again, like our scores. Like you saw, we had a lot of thoughts in like how to build our features, how to build our models, how to train them, how to combine them. And finally, we achieved to get the first place with an RC of 97 in comparison to second and third place with 93 and 89. So we saw like a huge boost in like building these like multiple pipelines, stacking them all together and making a final prediction. Going to the next slide. We heard a lot about limitations in terms of inference. Like it was a code competition. We had to submit code, which first we were limited in the file size. But second, we had only a single CPU core with 64 GB of memory. And this is like after the competition, like the competition was finished, we got the final scores on the leaderboard. We thought about, can we accelerate the inference? Can we make the inference faster? If you go to the next slide. This is in particular important in production systems because recommender systems, when we put them to production, they have to handle large throughputs with low latency. And why is that the case? If a single user goes to the website, you have like the user information or the user profile, and then you have to make the decision, or the system makes the decision, what should we recommend? And for that, you actually have to analyze all items which are possible, and it could be like 1 million to 1 billion items which you could recommend. Normally what happens, you have like some business rules, like for example, only from a certain area, or like some really fast models to crush it down to potentially only 1,000 or 100,000 items. And then you use the models we for example, developed in this competition to score them and then re-rank them to say like, oh, with the highest probability should be the first one, second highest the second, continues down. And that's what we receive, provide to the user. And there you see like a single user request can trigger 1,000 to 10 to 100,000 predictions, meaning like the recommendation models, they have a really hard throughput because every user request triggers so many recommendations, like so many prediction tasks. And that's the reason like the competition was set up having these constraints in terms of given compute, 1 CPU, 64 GB, and the latency constraint was around 6 to 8 milliseconds. And we wanted to know what happens, or like, can we accelerate it? Because if it's faster, we can build bigger models. We heard like design decisions Bo presented. We used a single GRU layers. We didn't use like BERT or transformers. We had to limit our number of models, or like number of trees of our XGBoost models. We had to limit like the features we built. So for us, the big question was like, if we can accelerate it, we could build bigger models with higher accuracy. And that means we could like even improve our scores. So if we go to the next slide. So, and that's what we did. And that's what we achieved. So we used GPUs to accelerate our inference, and we used a single A100 GPU, and it takes 5.5 minutes, like 5 minutes and 30 seconds, instead of 23 hours and 30 minutes on a single CPU. So we achieved a 260 times speed up using a GPU, which would enable larger models and a lot of more like data throughput. For fair comparison, we compared it to an 8-core CPU as well, and still achieved a 92 times speed up. It was 92 times faster. So how did we do it? I will talk a little bit in detail, but one common strategy is like we built the full pipeline from common pre-processing or like initial pre-processing, which Chris introduced in the beginning, to like feature engineering, to like model prediction, all on the GPUs. And there we used some open source library. All of these libraries are publicly available. So for the string processing and even like the BERT decoding, we used RecSys QDF, which is like a data frame library executing on the GPU. For all the disk I/O, we used RecSys QDF again and route it to packet files. As packet files are smaller, they're like compressed, so we can read and write faster. But compressing and decompressing it is on the GPU, so that's fast again. All the feature engineering is done on a GPU with QDF, like all the merged parts. For XGBoost, there's a special library, which is like QML forest inference library, which has like even a higher speed up than running XGBoost with the GPU mode. And finally, we used like neural networks, TensorFlow and PyTorch, the normal GPU stuff. But we used optimized data loader, which are directly on the GPU with NV-tabular and or DLPack. So I will talk some of the example in a second. We continue. But often the question would be like, okay, we use a GPU, but is that not more expensive? So our GPU accelerated inference was 92 times faster as the 8-core CPU, and it would be 8 to 9 times more cost efficient. So on the left side, we see a breakdown on the speed ups, and we see like each of the different component had a speed up from 60 to 160 times. Like the common preprocess 60 times, feature engineering, the highest one is XGBoost with 168, and overall we have a speed up 92 times. And each of the component is similar important as they require almost the same amount of time. As you may remember, we had like 5 different XGBoost models. Some of them were backed, some of them were like predicted per groups. So it's important to speed that up. And at the same time, the common preprocess, all of the parts like had an equally chunk. On the right side, you can see the dollar value estimated. So we run the 8-core CPU example on Google Cloud instance. It was the one Twitter recommended us, but instead of 16 cores, we used only 8 cores. To use not use the full memory. It's just cheaper. And running it for 503 minutes, it costs around $3. And in comparison, running an A100 instance on Google Cloud costs like $3.67 per hour. But running it only for 5 minutes and 30 seconds, it's around 34 cents. So we have like 100 times speed up. The costs are maybe 10 times higher, but that means in the end, we get an 8 to 9 times cost reduction. So at one time, we can either train larger model or we can save you money. Going to the next one. How did we do it? And in the end, it's only a few lines of code. This one is the example how to accelerate XGBoost with QML forest inference library. And you can see this is an example where the original XGBoost model was saved as a pickle file. So we have to load it and save it directly as an XGBoost model object. And then we can load it with forest inference library. One important part is all the features has to be data type float32. This is what you see in the middle of the line. So we convert it to float32 and then convert it to a QPy array, which is column-wise oriented. And that's it. And you can then run inference with the forest inference library even faster. If you go to the next slide. So this example is how to do how to accelerate the TensorFlow model with DLPack. And DLPack is a library which moves data on the GPU, like keeps the data on the GPU and can move it between libraries without it has to leave the GPU. So we read the data into the GPU with QDF from the disk. Then we convert it to a QPy array and then move it to DLPack. And then we can tell TensorFlow to get access to this to the data as a tensor, and then we can feed it to our model. So in that way, the data never leaves the GPU and can move it from one library to another library, and we can train our models directly way faster. Going to the next. And the last one is how to accelerate PyTorch. So NV-tabular is an open source library, and one part of it is an asynchronous GPU data loader. So it can read data from memory or even from disk and chunks it and does it asynchronously directly on the GPU. Same idea as before, the data never leaves the GPU. So read from disk, create our batch on the GPU, keep the memory data on the GPU memory and feed it to the data. If you look at the second part of the code, none of the code is different. You could use it with any kind of data loader. So you can just exchange your data loader with the PyTorch data loader and would run in the same way. Next one. That's the end of our presentation. Let me pass it back to Jim.
Chris, Bo, Jiba, and Benedict, thank you very much for spending your time speaking with myself and all the viewers. I think we all found this presentation enlightening and educational. You can learn even more about deep learning recommender systems by checking out episode 5 in the Grandmaster series, which includes some insightful Q&A at the end. As I mentioned at the top, I strongly encourage everyone to check out the paper that the team just published on this topic titled GPU-Accelerated Boosted Trees and Deep Neural Networks for Better Recommender Systems. The link is provided below in the summary. To all the viewers, thanks so much for spending part of your day with us and taking the time out of your otherwise busy schedule to enjoy this episode in the Grandmaster series. I'll leave you with the quote, "If you're the Olympic champion, then they have to wait 4 more years to get you again," which was said by Usain Bolt. However, in the realm of data science, we must continue moving at the speed of light because your competitors aren't going to wait to try to take the lead. I'm Jim Scott. Have a great day, and may all your data science be accelerated.